and today we talk about polarity. This was another special request from one of my students. This concept is currently the bane of their existence, so hopefully this video will clear a few things up for y'all. By definition, polarity is an unequal sharing of electrons within a covalent bond. So my electrons are being pulled one way or another within a bond. This is determined by the electronegativity difference. We talked about electronegativity in the trends video, about how that was how much an atom wants electrons, if I may use that terminology. So how much an atom pulls on those electrons, determined by the number of rings an atom has, how strong the nucleus is, how close they are to a full octet. And so when I say electronegativity difference, I literally mean the difference. In math, difference means subtraction, and this is just that. So in my classes, we have this wonderful little chart that actually has our electronegativities, since that is in fact a value that you can find. And so electronegativity difference is the difference between the electronegativities of two atoms within a bond. If the difference falls between 0 and 0.4, we call that a nonpolar bond, equal sharing. Everybody is playing nicely with all of their toys. If your number is between 0.4 and 1.8, that is a polar molecule. I usually describe it as a bully. Somebody is hogging the electrons. They're not pulling hard enough to yank the electrons off, so they're not taking their toys and going home. They're just hogging them. The electrons are spending more time around one atom than another. So when I'm talking about polar bonds, the polarity of the bonds themselves, I'm not talking about the whole molecule yet, just the bonds, one at a time. Again, we're going to look at the electronegativity difference. If our electronegativity difference falls in that polar range, we're going to use this symbol, an arrow with this little cross here at the back, which goes from the lower negativity to the higher negativity. E-neg stands for electronegativity, in case you missed that. So the positive end is towards the molecule, or the atom that is now more positive, because my electrons are being pulled towards my more electronegative atom. Again, we're not yanking them off, we're just hogging them. And this symbol is used to show where the electron density is moving within that molecule. If your electronegativity difference does not fall in the polar range here, it's nonpolar and we don't draw anything. If we want to determine whether or not our molecule is polar, so you've gone through and looked at each of your bonds individually, to figure out if our molecule is polar, we have to look at the whole picture, at all of the bonds. And we're looking for a net pull in one direction. And there's a couple of ways that can happen. The first way is if all of our arrows, like this, all my electronegativity density is all moving in the same direction. All my arrows are pointing one way. Another example is when we have one really electronegative atom that's kind of hogging all of the toys. The third scenario is perhaps you have one pull that is uncounteracted. So again, somebody being a bully and hogging the electrons. Then that means your molecule is indeed polar, and we indicate the positive side with a lowercase delta and the plus, and the negative with a lowercase delta and the negative. Incidentally, any time that I can identify one side as positive and one side as negative, that gives me two poles, one positive and one negative, which is called a dipole. Di meaning two poles, positive and negative. So that's all well and good, but let's do a few examples, and hopefully that will clarify things a bit. The first example I would like to do is BH3. Quickly, the structure for BH3 is about like that. And if we think about those two atoms, boron and hydrogen, just in terms of their placement on the periodic table, neither of them are terribly electronegative. Hydrogen takes a positive charge when he forms an ion, so he isn't really interested in attracting any more electrons. Boron has 3 valence electrons, so he could lose those 3, or perhaps he could gain 3 and have his 6, which is good. So he's also not terribly electronegative. So just by looking at the trends on the periodic table, I can already tell you that boron and hydrogen, this bond here, is going to be nonpolar because neither of these atoms are particularly gunning for those electrons. We can figure that out numerically as well. My chart tells me that hydrogen has an electronegativity of 2.1. Boron's is 2.0. So my electronegativity difference between those two when I subtract them, so since hydrogen's greater, we'll put that one on top. When I subtract the two, 2.1 minus 2.0, 0.1, that falls in our nonpolar range. So my atoms are sharing the electrons equally. Nobody is hogging the electrons. They're spending equal amounts of time around the hydrogen and the boron. So this is a nonpolar molecule. It also has nonpolar bonds. So in both cases, this is nonpolar. There is no pulling of the electrons in any which way, shape, or form. Our next example is water. Now water is a little bit strange because he does not follow our typical structure. If you know anything about Vesper, this is a bent structure. You might draw your Lewis dot structure straight across initially, but when I say go, and I let my molecule pop into 3 dimensions, as real-world molecules like to do, I get something that looks like this. According to my chart, that same chart that I showed you before, oxygen has an electronegativity of 3.5. Hydrogen is still 2.1. So let's see, if we do oxygen minus hydrogen, so it's 3.5 minus 2.1, I get an electronegativity difference of 1.4. That falls squarely in my polar range. My oxygen is far more electronegative than my hydrogen. So he is hogging my electrons. My electrons are moving towards my oxygen away from my hydrogen. This bond is exactly the same as this bond, so we're going to draw another arrow. So I have identified that I have polar bonds. Now to talk about the molecule, I have to see if all of my arrows are pointing in one direction. In this case, they are. My arrows are all pointing down towards the bottom of this molecule. So that means right about here, I can actually draw a line if I wanted to and designate this side of the molecule as negative and this side of the molecule as positive. So this guy is in fact a polar molecule with polar bonds. Let's see if I can fit another example in before my time runs out here. CF4. I'm going to hurry a little bit. So this guy, lots of electrons around the outside here on my fluorines. Fluorine, if you remember from the trends video, is the most electronegative atom on the entire table. So without even doing my subtraction, I can already tell you that fluorine is going to pull those electrons away from my carbon. So my electrons are moving away from my carbon, leaving that positive end towards the carbon there. And you'll notice my arrows are going every which way. I have equal pulls going to the left and right, and equal pulls going up and down. This is what I meant by uncounteracted pulls. In this case, every pull has an equal pull going in the opposite direction. I have no one side of my molecule that is positive and no one side that is negative. So even though I have polar bonds in this molecule, this is a non-polar molecule because I have no net pull in one direction. If these were all flipped around and all my arrows were pointing towards the center, as long as all 4 sides are equal, I would have an equal but opposite pull on each side of that carbon. The middle does not count as a side. We need one side or the other of a molecule to be identifiable as positive or negative. Ooh, I think I have time for at least one more example. Here we go. So, carbon trihydride monochloride. Now, depending on how you draw this, your Cl might end up on a different side than mine, but that's okay. I'm going to put it over here on the right. So we already know that hydrogen was 2.1. Where'd my chart go? There it is. Carbon is 2.5. Chlorine is 3.0. So I've got two different types of bonds here that I need to look at. I've got carbon and hydrogen, and I've also got chlorine and carbon. So let's see. Carbon and hydrogen falls right on that polar-nonpolar border. Chlorine and carbon falls on the other side of that band, that polar band. So this is in fact polar. So I have one really electronegative atom that is pulling in that direction. So this is what I meant by uncounteracted pull. That carbon is pulling all of the electrons away from my hydrogens, away from my carbon, and towards the chlorine. So this is a polar bond, and it is in fact a polar molecule. So you need to be extra special careful to make sure that your whole molecule is polar. I have an uncounteracted pull in one direction, or all my arrows are pointing in one way. Best of luck with polarity. See you next time.